Welcome to Theory of Computation. This is lecture number 13. Today we will mostly discuss a concept in mathematics and computer science called reducibility. Basically the idea is as following. Suppose we have two problems. What we want to do is we want to take problem A and somehow reduce it to problem B in such a way that the solution for problem B can be used to obtain a solution for problem A. This is a concept that is widely used in mathematics and computer science. Very often, when you're given a problem, what you do is you change the problem enough so as to bring it into a form that is familiar. That's a problem that you already know how to solve. At that point, you stop working and you just say that since I know how to solve this problem that arises from this, I have already solved the original question. For example, suppose somebody gives you a complicated optimization problem and they ask you to optimize this function. Well, you set up some equations for that and eventually you solve these equations, and suppose finally you realize that you can solve the problem if you were to solve a given quadratic equation. At this point, you can actually stop and claim that you have solved the original problem, because you will argue that I already know how to solve a quadratic equation. So, if the question does not really ask me to show the solution but just to convince somebody that I can solve the problem, then I can stop at this point. This is the basic concept of reducibility. Actually, there's a very nice joke about reducibility. The joke is as follows. There is a conference, and in the conference there are three people. One engineer, one physicist, an experimental physicist, and the third one is a theoretical computer scientist or a mathematician. And they are attending the conference, and at the first night of the conference, the trash can in the room catches fire, and the engineer wakes up. When he sees the trash can on fire, he goes to the bathroom, he brings a bucket of water, he throws it in the trash can, he goes back into the bathroom, brings another bucket, throws it in the trash can, does that about 3 or 4 times, almost floods the whole room, then screams a lot saying that there is a fire, goes and turns on the fire alarm, and then informs all the people in the hotel that there was a fire. Well, so the problem of having the fire in the hotel room is solved this way by an engineer. The next day also, there's a fire in the room, a fire in the trash can, and this time the experimental physicist wakes up. He looks at the trash can and realizes that there's fire in the trash can and this could be dangerous. So he goes into the bathroom, picks up a glass of water, and carefully measures about half a glass of water, comes back and carefully pours this water on the trash can so the fire is completely extinguished, and then he makes a note in his notebook and he writes how many milligrams of water were needed to put out the fire. And the next day he goes and reports the incident. The third day, once again, there is a fire in the trash can, and this time the mathematician wakes up and he looks at the trash can and realizes that it's on fire and this could be dangerous, so he wants to solve the problem. So what he does is he simply wakes up the physicist, thereby reducing the problem to an already solved one. So this is the spirit of reducibility. Instead of solving the whole problem, you just change it enough to change it into a familiar problem which is already solved, and thereby you show that in principle you can solve the original problem. So today we'll study the concept of reducibility, in particular something called mapping reducibility. We will then use this concept to show that many problems are undecidable. After that, we will show that some problems are not Turing recognizable. So, following is the overview of today's lecture. First, we will look at computable functions. After that, we will define mapping reducibility. Then we'll see applications of mapping reducibility to undecidability theory. And in the last part of the lecture, we would show some applications of mapping reducibility to un-Turing recognizability, or we will show that there are certain languages which are not Turing recognizable using this concept. So let's begin. So last time we briefly discussed what a computable function was. A computable function is simply a function that can be computed by some algorithm or some Turing machine. So imagine a Turing machine, the one shown in the diagram. This Turing machine has an input tape. It also has an output tape. When you put the string X on its input tape and turn on the machine, if this machine runs for a while and eventually halts with f of x written on its output tape, we will say that this Turing machine computes the function f. So in order for you to say that a function is computable, you must be able to define a Turing machine which on input x will produce exactly f of x and halt. Or in other words, what you would need to do is describe an algorithm for computing this function f. So computable functions are exactly those functions which can be computed using some algorithm. Let us have a look at some examples. Let us consider a function which goes from sigma star to sigma star. So the function as input takes strings and it produces strings. We will say that f is computable if there is a Turing machine M such that on every input w, it halts by writing f of w on its output tape. Note that in some books, the machines are not required to have a separate output tape. So you could equivalently define computable functions as functions for which there is a one-tape Turing machine, and when you put w on the input of that Turing machine, the machine computes for a little while and eventually halts after writing f of w on its only tape that it has. So we will call these functions computable functions. Most of the functions you have studied are computable functions. Let's look at some examples. So for example, here's a function which takes two pairs of numbers m and n. So actually it takes an encoding of the pair m and n and produces m plus n, or an encoding of m plus n. This is simply the addition function which takes two numbers and outputs their sum. This function is computable as you have studied many algorithms. In fact, you have studied an algorithm in your elementary school. So this is an example of a computable function. Let's look at another one. Suppose A is an n by n matrix, then the function that maps f of a to a squared is computable. So in this case, you're given a matrix and you're asked to square this matrix. Since you know an algorithm for multiplying two matrices, you can simply apply that algorithm to a and get a times a, which will be the square of this matrix. So this function is also computable. Actually, computable functions are very important in practice. In fact, when we are thinking about practical problems, computable functions are more important than languages. In languages, all we are trying to do is to answer a question yes or no. But in practice, what we have is computational problem where we give an input and get another output, which may be an answer yes or no, or it may be much more complicated thing. For example, we may be giving as input the positions and velocities of certain particles, and what we would want to do is to compute what would be the positions and velocities of these particles after a certain amount of time. So in this case, we're not asking a yes-no question. We actually would want an algorithm which would take all this data and produce data which tells us where these particles will be at a different time. So we're more interested in computable functions when we're talking about practical problems. For example, you may be interested in taking a matrix and another matrix and computing the product of these two matrices. In this case, you are not trying to solve a yes-no question, so the question cannot be properly posed in terms of languages. However, it can be posed very nicely as a computational problem. You want to compute a function f which takes as input two matrices A and B and outputs their product A times B. So, is that function computable? Well, yes, you have studied algorithms for matrix multiplication, so this is also a computable function. Now what we want to do is use this concept of a computable function to define reducibility. So roughly, suppose we have a problem A and we have another problem B. We will say that the problem A is reducible to B if we can somehow change the problem A into the problem B by using a computable function. So suppose you have two problems A and B. Roughly, if the solution of B can be used to solve A, then we say A is reducible to B. So what does it mean? The solution of B can be used to solve the solution of A. Well, there are many notions of reducibility, and we will start with a very simple notion called mapping reducibility. Some examples of reducibilities, let us look at them now. Let's say that we have two problems. First problem is that you want to reach from a point A to a point B in Lahore. You can reduce this problem of finding how to go from point A to point B to the problem of finding a map of the city. Okay, so this is an example of a reducibility. The problem of crossing a river can also be reduced to the problem of finding a boat. If you have a boat, then you can cross a river. So if you're standing at a river and you want to cross that river, that problem can be solved if you can find a boat. Another way of thinking about reducibility is if one wants to quench one's thirst, then they can reduce this problem to the problem of finding clean water. So if you're thirsty and you want to quench your thirst, you can find clean water and solve that problem. Of course, that's not the only way to solve that problem. You may be able to find, for example, some other soft drink and quench your thirst. However, when you find water, that solves your problem of being thirsty. Another example is, suppose you have a quadratic equation that you want to solve. Well, the problem of solving a quadratic equation can be reduced to the problem of finding a mathematician and making friends with them. So that is an indirect way of solving a quadratic equation. You don't have to learn how to solve a quadratic equation, but just find somebody who knows how to solve them and make good friends with them so they would take your quadratic equation and solve it for you. So this is the concept of reducibility. Let us say A is a language. We will say that A is mapping reducible to B, and we'll write it as A is less than or equal to B with a subscript M under the less than or equal to if there is a computable function f such that for every W, W is in A if and only if f of W is in B. So we will say that a problem A is reducible to B if I can find a function that maps strings into strings, and whenever a string happens to be in A, the corresponding string produced by this function will happen to be in B. Whenever the string is not in A, the corresponding string produced by this function will not be in B. Let us look at a diagram. In this diagram, the left side shows sigma star, the set of all inputs, and the shaded portion shows the set A. The right side again shows sigma star, and the shaded portion now shows the set B, or the language B. The function must map all strings inside A into B. So all the strings that belong to the left shaded portion must go into the right shaded portion. It must also map all the strings inside A complement into B complement. So all the strings that are not in the shaded portion on the left side must go in the portion which is not shaded in the right side. And this function must be computable. So you see, f is a function that reduces the problem A into B. What that means is, now if somehow I can manage to solve B, I would have produced a solution for A. Let's continue. We have to make few observations about this function. Note that we are not requiring this function to be one-to-one. So it is allowed to map several inputs into one single input. Furthermore, this function is not needed to be onto. We are not requiring this function to be onto. So this function does not need to exhaust all its domain. So this function can map 2 points to the same point. Furthermore, there can be things in sigma star which are never hit by the function. So it is not a requirement for this function to be one-to-one or onto. It's not required. The only thing that is required is the things that are in A must be mapped into things that are in B, and strings that are not in A must be mapped to strings that are not in B. That's the only requirement that we asked of this function. And one very, very important requirement is that this function should be computable. We should be able to compute this function by using a Turing machine or an algorithm. Let us look at an example of a reducibility. Let's take A to be the set of all integers n written in binary such that n is even. And let us take B to be the set of all strings which do not contain a 1. So A is the set of all strings which, when we read them as binary, are even numbers. So another way to think about A is these are the set of all strings over zeros and ones that contain a 0 at the end, at the right end. B is the set of all strings that have no zeros. Now let's define a very simple reducibility from A to B. Let us define this function which takes a string x1, x2 all the way up to xn and just outputs xn, the last bit or the last character of this input. Is this function computable? Well, it's very easy. You can design a simple Turing machine that reads its input, finds out the last character, erases everything, and then writes the last character on its output tape. That's very easy. So this function is computable. The other thing is it will map all strings of A into one string, namely 0, which happens to be in B. So it maps all strings of A into strings which are in B or a string which happens to be in B. On the other hand, if a string is not in A, then it'll have a 1 at the end. All those strings will be mapped to 1, which is not in B. So this function shows that A is reducible to B. Now suppose that A is reducible to B and B can be solved. Then we can reduce A to B and we can solve B. Therefore, we can conclude that we can solve A. That is the essence of reducibility. If A is reducible to B and somehow you manage to solve B, then you would have solved the problem A. So let's prove the next theorem. This is a very important theorem. This is the central theorem about reducibilities, and it says that suppose A is reducible to B and B is decidable, then A is also decidable. So how can we use this theorem? Well, if you know that a problem B is decidable and you have a new problem A that you don't know anything about, if you somehow manage to reduce A to B, then you can conclude that A is also decidable. How will we prove this theorem? The theorem is extremely easy to prove. All we have to do is take the problem, reduce it, and use the solution that we have for B in order to solve A. Let's see how the formal proof goes about doing this. Well, what we want to do is we want to prove that if A is reducible to B and B is decidable, then A is decidable. So let's take a set B which is decidable and let's say that A is reducible to B. Since B is decidable, there is a decider M that decides B. Now we consider the following decider N. On input X, this decider computes Y equals f of X. Then it runs M on Y. If M accepts, it accepts, and if M rejects, it rejects. So this decider is not doing anything. All it does is it takes its input, applies the function f, which reduces A to B, and then simply runs M on the output of this function. Let's see what this new Turing machine N does. Since f is computable and M is a decider, therefore N is a decider. Since M halts on all inputs and f is computed by a Turing machine which halts on all inputs, therefore N will halt on all inputs, and hence N is a decider. Furthermore, if X is accepted by N, if and only if Y is accepted by M. However, Y is accepted by M if and only if Y is in B. Why is that? Because M accepts B, so it accepts exactly the strings that are in Y. From this, we can conclude that X is in A if and only if Y, which is equal to f of X, is in B, which implies that N accepts X if and only if X is in A. Hence, the language of N is exactly equal to A, and N halts on all inputs. This shows that A is also decidable. So, although the formal proof was slightly cumbersome, but the basic idea is very, very simple. If A is reducible to B, then there is a reduction, F, which reduces A to B. What we can do is, in order for us to solve A, we take an input, use the reduction, and then use the solution for B to solve A, or use the Turing machine or decider we have for B in order to construct a decider for A. So, this theorem says that if A is reducible to B and B is decidable, then A is decidable. Well, we can write this theorem in the contrapositive form also. Suppose that A is reducible to B and A is undecidable. Then we can conclude that B is undecidable. And this is the form that we are going to be more interested in. So, this theorem can allow us to prove that problems are undecidable. The way we do that is, suppose we have a problem which we suspect is undecidable. We take an already known undecidable problem and reduce that to our problem. If we can do that, then we will be able to show, then we would have shown that our problem is also undecidable. Suppose that you have a language P and that you do not know anything about P. You're wondering if P is decidable or undecidable. There are two approaches you can take. First, you can find a decidable language D and then show that P is reducible to D. If you can do that, then you can conclude that P is decidable. The second approach is you can find an undecidable language U and show that U is reducible to P. If you can do that, then you can conclude that P is undecidable. So now, reducibility gives us two options. One is we take a new problem and we can show that it is decidable by reducing it to an already known decidable question. On the other hand, we can also try to reduce an undecidable problem to P, and that way we'll be able to show that P is undecidable. One thing you have to be clear, suppose somebody tells you that A is reducible to B. That does not give you any information. That statement that A is reducible to B does not give you any information about whether A is decidable or not, or whether B is decidable or not. In itself, that statement does not say this about the decidability or undecidability of either A or B. It's only when you add something else to that information. So, for example, if somebody comes along and proves that B is decidable, you can immediately conclude that A is decidable. Similarly, if somebody adds the information that A is undecidable, you can immediately conclude that B is undecidable. So, in some sense, reducibility tells you about the relative difficulty between the two problems, but it does not tell you anything about the difficulty of solving either of the problems individually. For that, you have to do more work. Suppose that you have a problem P, you have a language P that you don't know anything about. Well, it could be either decidable or it could be undecidable, and you do not know whether it is decidable or undecidable. If you suspect the language is decidable, you can either try to come up with an algorithm or a Turing machine that decides this language, or you can try to reduce this problem to a problem that is already known to be decidable, and this way you will prove that P is decidable. On the other hand, if you suspect that P is undecidable, then what you would do is you would find an undecidable question and reduce that undecidable question to your problem P, and thereby showing that your problem P is also undecidable. But which approach should you take, and which problem you should choose in order to reduce that problem to your problem or reduce your problem to that problem? Furthermore, how would you come up with this reducibility? All these are very interesting questions, and in general, there is no fixed answer. There is no recipe, there is no algorithm, there is no method that tells us which approach to take. In fact, let's look at this thing and think about Hilbert's 10th problem. Hilbert posed his 10th problem in 1900s. Many mathematicians worked on this problem. For 70 years, they were not able to come up with an algorithm. Since so many mathematicians could not come up with an algorithm for 70 years, was it not enough to say that the question was undecidable? Well, no, we had to prove that the question was undecidable. So mathematicians actually, after a little while, started looking for a proof of undecidability of Hilbert's 10th problem. Eventually, Jure Matijević was able to reduce Hilbert's 10th problem, and once again, if one follows the chain of reductions that he did, we realize that what he showed was if Hilbert's 10th problem was decidable, then halting problem would also be decidable. So in some sense, he gave a very complicated reducibility from the halting problem to the Hilbert's 10th problem, thereby showing that the Hilbert's 10th problem is undecidable. It took him 70 years. So in general, these problems can be extremely difficult. Some reducibilities are very difficult to find. They're very complicated, and ingenious methods are used to actually construct these reducibilities. In other cases, reducibilities are quite straightforward. In this course, we will not be dealing with very difficult reducibilities, but we would want to deal with reducibilities which have some moderate amount of difficulty. Note that to prove the decidability of P, we reduce P to a known decidable problem D. We show that P is reducible to D. To prove that P is undecidable, we reduce U to P, where U is a previously known undecidable problem. We show that U is reducible to P. When we are showing that P is undecidable, we use the reducibility backwards. We don't reduce our problem to an undecidable problem. That would not show anything. Suppose that P is reducible to an undecidable problem. That does not show or tell us anything about P itself. But when we take an undecidable problem and reduce it to P, only then we can claim that P is also an undecidable problem. Here, I would like to say a little bit about the notation that we are using. Remember that if A is reducible to B, what we are writing is A is less than or equal to, there's a little M sign there which stands for mapping reducible, but let us ignore the M sign. We're saying A is less than or equal to B. You should read this as A is easier to solve than B. Now suppose, and what we do is we think of decidable problems as easy problems and undecidable problems as hard problems. Now suppose that you show that A is less than or equal to B, which we read as A is easier than B. Now if B is a decidable question, then since A is easier than B, therefore A is also a decidable question. On the other hand, suppose that you show that U is easier than P, which we can, if we read backwards, we can be saying that P is harder than U. Now suppose U is undecidable, then since P is harder than U, therefore P must be undecidable. Notice that these are just cues for you to remember how to use reducibilities. These are not formal definitions. However, the notation has been chosen in order for you to make it easy for you to remember how to use reducibilities. Reducibility shows that problems are decidable when you reduce a problem to a decidable problem. When you take an undecidable problem and reduce it to your problem, you show that your problem is undecidable. And this notion of reading the sign as easier than, or reading when you read it backwards as harder than, does work in this case. Mapping reducibility is only one kind of reducibility. In some sense, it is the simplest way to reduce one problem to another. There are other kinds of reducibilities, but we will only be discussing mapping reducibility. Actually, we have been using mapping reducibilities in order to show that problems are undecidable without explicitly saying that we are using mapping reducibilities. Since we are already familiar with those proofs, now let us quickly go through some of the proofs using mapping reducibility. Here, of course, we will revise our proofs and we will also identify how we are using mapping reducibility in order to show that problems are undecidable. Well, let's remember ATM, our most fundamental undecidable problem. The problem that we first showed was undecidable. Then we looked at another problem called halt TM. Remember that ATM, you were given a Turing machine M and W, and M comma W belongs to ATM if and only if M accepts W. On the other hand, halt TM consists of pairs M comma W where M halts on the input W. What we did was we showed that if we could solve halt TM, then we could also solve ATM, thereby showing that halt TM was undecidable. Let's redo this proof. Suppose that we can show that ATM is mapping reducible to halt TM. Then we can use our previous theorem to conclude that halt TM is undecidable. So let us look at this proof which uses mapping reducibilities explicitly rather than implicitly. We have our fundamental problem ATM, which is the set of all encodings of M comma W where the Turing machine M accepts the string W. Now let us consider halt TM, which is the set of all strings M comma W where the Turing machine M halts on W. We want to show that ATM is mapping reducible to halt TM. So what we have to do is find a computable function f such that f of M comma W will be equal to M prime comma W prime such that M comma W is in ATM if and only if M prime comma W prime is in halt TM. So M will accept W if and only if the Turing machine M prime halts on W. Let's look at the description of the function that computes this reducibility. Let us look at this machine f, which computes the function as follows. On input M comma W, it constructs M prime as follows. M prime is a Turing machine whose description is given in the quotes. Note that this function will only construct the description of M prime. It would not run M prime or anything like that. It will simply plug in at various places in this M prime, so it'll just make syntactic changes. By looking at M, it'll produce a new Turing machine M prime. It will not be running this Turing machine M prime. Let's look at this function. So M prime is constructed as follows. On input X, what we do is run M on X. If M accepts X, then M prime will accept its input. If M rejects X, then M prime will loop forever. So M prime is just going to be a syntactic code in which M is plugged in at some point. This would be the description of M prime. The function will actually output M prime comma W. Now it is easy to see that if M accepts W, then M prime is going to halt on W. On the other hand, if M does not accept W, then M prime is not going to halt on W. Therefore, this function is a reducibility from ATM to halt TM. Since we already know that ATM is undecidable, this shows that halt TM is also undecidable. So this proof that shows that halt TM is undecidable uses an explicit reducibility. Let us look at another example. Remember that we showed that ETM was the set of all Turing machines or encodings of Turing machines which accept the empty language was also undecidable, and we also showed EQTM was undecidable. EQTM was the problem where you're given two Turing machines and the description of two Turing machines belongs to EQTM if and only if they accept exactly the same language. So in this theorem, all we will do is we will show that ETM is reducible to EQTM. So in some sense, telling whether the language of one given Turing machine is empty in some sense is easier than telling if the language of two Turing machines is the same. So let's look at this reducibility. Let M1 be a fixed Turing machine that rejects all possible inputs. So you can design this Turing machine M1 which will have only two states, and its first step will be just to go into the reject state. So this Turing machine will reject all possible inputs. Now suppose we define a function in the following way. Suppose we define f of a Turing machine M to be M, M1. Then the language of M is going to be empty if and only if the language of M is equal to language of M1. See, M1 is the Turing machine that rejects all inputs, so it accepts the empty language. So what we're saying is a triviality, that the language of M is empty if and only if the language of M is empty, which happens to be the language of M1. So this function actually reduces ETM, the emptiness problem, into EQTM, the equivalence problem for two Turing machines. All we have to do is just convince ourselves that this function is computable. But this function is clearly computable, since if I give you a description of one Turing machine, you can easily design a Turing machine that outputs the description of that Turing machine followed by the description of M1. Of course, M1 will be hard-coded. So the Turing machine that computes this function will have the description of M1 hard-coded in it. This was once again an example of an explicit reducibility. Let us look at another reducibility which is going to be slightly different now. What we will show is ATM, the acceptance problem for Turing machines, is mapping reducible to the complement of the emptiness problem. So what we want to show is ATM is mapping reducible to ETM complement. In order to do this, what will we have to do? Let's have a look. We want to come up with a computable function f such that f of m, or f of the description of M, is the description of another Turing machine M1, such that if M accepts W, then the language of M1 is not empty. And if M does not accept W, then the language of M1 is empty. If we can show such a computable function, we would have mapping reduced ATM to the complement of the emptiness problem. Well, what we need to do is somehow come up with a description of this Turing machine M1, which will have the property that we have described already. Let's see how we can output this Turing machine M1, or what does this description of this Turing machine M1 look like. The description of this Turing machine is given as follows. M1 on input X will first compare X with W. W is of course going to be hard-coded in M1. If X is not equal to W, it rejects X. Otherwise, it runs M on X. If M accepts X, then M1 will accept X. So this Turing machine, what it does is compares its own input X with a hard-coded input W. If its own input is not equal to W, it simply rejects. Otherwise, what it does, it runs M on X, which is equal to W, and accepts if M accepts X. So, what will be the language of M1? Let's have a look. The language of M1 is not going to be empty if M accepts W. On the other hand, the language of M1 is going to be empty if M does not accept W. So, the previous reducibility shows that ATM is mapping reducible to the complement of ETM. So, what have we been able to show? We've been able to show that the complement of the emptiness problem for Turing machines is undecidable. How did we conclude that? Since ATM is undecidable and ATM is reducible to the complement of ETM, therefore the complement of ETM is undecidable. From this, we can also conclude that ETM is itself undecidable because we have already proved the following theorem, that A is decidable if and only if its complement is decidable. So since ETM complement is undecidable, its complement, which is ETM, that is also undecidable. So now we have added another tool to our repertoire. Sometimes what we can do is show that a problem is undecidable by reducing an already known undecidable problem to it, or we can reduce an already known undecidable problem to the complement of our problem, and that also shows that the problem that we have at hand is undecidable. So we have actually expanded our techniques a bit more. In order to show that a problem at hand is undecidable, we can reduce an undecidable question to it or its complement. Let's continue. Let's now look at what reducibility has to say about Turing recognizability. We claim that if A is mapping reducible to B and if B is Turing recognizable, then A is also Turing recognizable. Remember, I told you that you can read this less than or equal to sign as saying that A is easier than B. Now suppose you know that B is Turing recognizable, then since you can reduce A to B, therefore A is also Turing recognizable since it is an easier problem. So you can consistently read this notation as being easier than. However, in order to read it as being easier than, remember that we are not saying it's easier to solve in any sense other than computable and not computable. It is possible for a problem A to be reducible to B, and you can solve A faster than B, but that's not what is being discussed here. All we are saying is that if B happens to be decidable, A would also be decidable. If B happens to be Turing recognizable, then A would also be Turing recognizable. How will we prove the theorem that we have just stated? Well, the proof of it is almost identical to the proof of the previous theorem. The only change is remember in the previous theorem we said since B was decidable, there's a decider which decides B, and we took that Turing machine M. Well, now we don't know whether B is decidable or not. However, we know that B is Turing recognizable. So we will take the machine M that recognizes B and essentially repeat the proof. Let's have a look at it. Suppose that A is reducible to B, and let F be the reducibility from A to B. Furthermore, since B is Turing recognizable, there is a Turing machine M such that the language of M is equal to B. Now let us consider the new Turing machine N. On input X, it computes Y, which is equal to f of X. Then it runs M on Y. If M accepts, then N accepts. It is easy to see that the language accepted by this Turing machine N is exactly the same as A. However, we cannot claim that this Turing machine N is a decider, since M is not a decider. All we can say is N accepts the language A, and therefore A is Turing recognizable. Of course, we will be more interested in using this theorem in its counterpositive form. So let us look at this theorem in its counterpositive form. Let us explicitly state the counterpositive form. If A is mapping reducible to B and A is not Turing recognizable, then B is not Turing recognizable. So once again, we can use this theorem to prove that there are certain languages which are not Turing recognizable. Let us use this theorem to prove something very, very interesting. Remember that we have already shown that ATM complement is not Turing recognizable. We did that in the first part of the course, and I can remind you of its proof. Well, what we did was we proved that if a language A is Turing recognizable and its complement is also Turing recognizable, then the language must be decidable. On the other hand, we also proved that ATM was not decidable. But since ATM is Turing recognizable, therefore its complement must not be Turing recognizable. So we know that ATM complement is not Turing recognizable. Let's use that fact along with this theorem and the concept of reducibility to come up with some interesting theorems. Let's recall that EQTM, which was the problem where you're given the description of two Turing machine and the pair M1, M2 is in EQTM if the language of M1 is equal to language of M2. So this is the equality problem for Turing machines. Given two Turing machines, we have to tell whether they accept exactly the same language. What we're going to show is that this problem is neither Turing recognizable nor its complement is Turing recognizable. Let's start. Let's show that ATM is mapping reducible to EQTM. Well, suppose you're given the input M, W. We can make two Turing machines. One Turing machine is M1, which on input accepts everything. So M1 has the language sigma star. It accepts the language sigma star. M2 on input X will run M on W. If M accepts W, it will accept X. So M2 will accept all its input if M accepts W. So the language of M2 is going to be sigma star if M accepts W, otherwise it's not going to accept anything. Well, what if we map M, W to M1, M2? Then if M accepts W, the language of M1 is going to be equal to the language of M2. And this shows that ATM is mapping reducible to EQTM. Let's now prove something more about this problem. Now suppose you're given the pair M, W. Let's consider now these two other Turing machines. M1 is the Turing machine that rejects everything. So M1 accepts the empty language. M2 is the following Turing machine. On input X, it will run M on W. If M accepts W, it will accept. So the language of M2 is going to be empty if M does not accept W. So now let us map the pair M, W to this pair M1, M2. If M does not accept W, then the language of M1 is going to be equal to the language of M2. Hence, this function f is a reducibility from the complement of ATM to EQTM. This function can be computed as follows. On input M, W, we construct M1 and M2 as described above, and we just output pair M1, M2. So what have we shown? We have shown that ATM is reducible to EQTM. We've also shown that the complement of ATM is reducible to EQTM. Well, from the first fact, since ATM is reducible to EQTM, we conclude that ATM complement is reducible to EQTM complement. Therefore, the complement of the equality problem must be not Turing recognizable. So the complement of equality problem is Turing unrecognizable. On the other hand, since ATM complement is also reducible to EQTM. Therefore, EQTM is also Turing unrecognizable. So here we have an example of a problem whose not Turing recognizable and its complement is not Turing recognizable. This is the first such question we have seen. We have seen a language which is itself not Turing recognizable and whose complement is not Turing recognizable. This is extremely interesting, a problem which is so difficult that we cannot even recognize the problem or the complement strings in the problem. Well, in the next lecture, we will once again look at reducibilities and we will look at how we have been using reducibilities and what can we do more with it. I'll see you next time. Thank you and goodbye.